So we are on this problem counting bits. Given an integer n, return the array answer of length n plus 1 such that for each I from 0 to n, which would be n plus 1 elements, answer I is the number of ones in the binary representation of I. For example, if we have 2, then we have numbers from 0, 1 and 2. Their binary representation would be 0, this would be 1, and this would be 1 0. The number of ones in the representation is 0, 1 and 1, which is given over here, and that would be our output. Similarly, for n equals to 2, we have these binary representations. We have 0 number of ones, we have 1 number of 1, again 1, and then 2, and then 1, and then 2. N can be 10 power 5, which is a very large value. A naive approach to solve this problem can be, let's look through all these values and calculate the number of ones. And that we can do. Let's say we have 1 0 1 1 0, we have something like this. We can calculate the number of ones by multiplying this with 1. If this gives us a 1 in the output, which means that the element at the end is a 1, and then we can shift this right. So this would become 1 0 1 1, multiply that with 1. We have 1 over here, and we shift it. In this case, we had a 0, and we shift it, and we continue doing that, which means we would take the number of iterations equals to the number of bits over here. We would continue doing that until this entire thing becomes 0. Now this is taking a lot of iteration. If we have something as big as 10 power 5, this would take a lot of iterations. Can we solve this problem in O of n? To do that, we need to make some observations. Let's say I have n equals to 8. So this would be the representation of numbers from 0 to 8. We can make this observation that for every even value, the number of ones is similar to the number of ones in the half of that even value. So from 4, the number of 1 is 1, and half of that is 2, and the number of ones is also 1. We can validate that with 8, like 8 is very similar to its half, which is 4. Now, why is this true? Why is this observation true? Because in binary numbers, these values are 2 power 0, 2 power 1, and 2 power 2. When a 1 is shifted from, let's say, this position to this position, the overall number increases by 2 times. So 2 written as 0 1 0, if this 1 shifts to this third position, which happens in the case of 4, its value is doubled. So to double this value, you don't need to add another 1. You need to just shift that 1. Very similarly, from 4 to 8, this 1 is in third position and that shifts to fourth position and the number is doubled, which is 2 power 3. Another observation we can make with odd numbers. Let's take 3. The number of ones in 3 is 1 more than the number of ones in the number just before that. It is true for 3. It has two ones, and over here it has 1 1. We can make that observation for 5. It has 2, and the one above has just 1. We can make this observation for 7. Very similarly, 1 more than the previous one. Now, why is this observation true? Because if you write binary numbers, every time we create an odd number, because all of these actually give us something even. So even plus even would be even. But this over here gives us odd. So every odd number is actually made up of even numbers plus this odd number. So every time we have an odd number, the previous even number is added with 1. And that's how the odd number is created. So if 7 depends on 6, so on 6 we can add one more 1, and that would be number of 1 in 7. How does 6 get its value? So from 6, since it's an even number, how about we go to its half? From 6 we go to 3. 3 has two ones and 6 has two ones. This validates the even case too. So once we have this observation in place, we can say that for even number, we look at their half. Their half can be an odd number, it can be an even number. For an odd number, we look at the number just before it, or we can make another observation that the number just before the odd number is actually even number. So how about we go to its half? Instead of looking that number over here 6, how about we make two jumps? Because anyways the number of 1 would be similar. So instead of looking at 6, we can look at 3. So this over here would be our general algorithm of solving this problem in O of n. Let's take a look at the code implementation. So I am here in the code editor. I am given this function count bits. It receives a number n. Let's initialize a result array. I'm assigning it 0. At later point in time, I would add values to it. So I'm calling it that I have 0 number of ones at this point in time. And the size would be n plus 1 from 0 to n. Then I would traverse through this result. So for I in range n plus 1 from 0 to n plus 1 number of values. Now I need to check if it is an odd or an even. So if I mod 2, if this gives me a 0, it's an even number. In even case, what do? We say that the number of ones is same as the number of ones at half of its value. So result I is equals to result of I divided by 2. In the first case, it would be 0, but at later point in time, the number of 1 at I would be the number of ones at I by 2. And I'm doing an integer division because I don't want float values inside in the form of an index. Else, if it is odd, result I would be equals to result of the half of the number before it, before the odd number. So the number before the odd number would be I plus 1. So half of this number, since I plus 1 is even, we know that, and plus 1, because every odd number adds one more 1 to the previous. And in the end, we can return the result over here. Let's try to run this code. Let's submit it. So we have a solution over here.